Okay, so today Aziz Kharoof from the University of Haifa is going to talk about simplicial distributions, convex categories, and contextuality. So this is the second talk in the simplicial distributions seminar. So Aziz, you can go ahead.
Thank you, Gian. Thank you. Okay, I will start. Hi, everyone. I'm writing the title, Simplicial Distribution, Convex Category, and Contextuality. So let me remind you what is a simplicial distribution. Actually, simplicial distribution, we are encoding some outcome probabilities. Like outcome probabilities. Is encoded. They come from some, physical phenomena. Okay, we will not going to talk about it already. Jihan talked about that. Okay, encoding in one morphism, right? In one map. The y, where x is this morphism in simplicial sets. Okay, so x is a simplicial set, and y is a simplicial set. Let's say this is the category of simplicial sets. Okay, both of them in simplicial sets, and this morphism actually in simplicial sets. So what we have actually, let me remind you. So what we have actually, we have for every, what that mean? Like for every, let's say n simplex in X, we have a distribution, right? Let's call it P sigma distribution where in dyn. Okay, let's focus ourselves as Gian did last time when y is delta zm. Okay, you remember what it means, delta zm? Delta zm, when we have, let me write in the side, delta zm is this simplicial, say when we have in the 0 degree zm here, zm cross zm 3 times, and so on. And the faces is important. The faces, of course, the degeneracy is also important for the theory, but it's important for applications. The faces. So we have two faces here, which coming by deleting. Like we can delete like A, B. We can go by deleting the first one, which is D0. D0 we going to A, and by D1 we going to no, it's the B to B. We deleting the first one, and we deleting the second one. We going to A. The same here. We have 3 options to delete, so we have 3 maps here. Okay. We of course we have also the jersey map by copying. Say, okay, it's not important for now. Okay, so we will replace by this. So this will be like P sigma when we have n n simplex. This will be z m n plus 1 times, right? Because you see, like in the 0 degree, it's 1, and the 1 degree is 2. So which it's mean like when we have n, like so let's say we have a triangle, it's like sigma is representing this triangle. That means that what is that mean? If we back to what Jihan explained last time, it's mean like there is 3 measurements that we can do together, right? We can use together, and we get the probability distribution about the where in M3, this in X2. Okay, so for this we will get, for this together we will get the distribution here. Okay, because this all the outcome can be for this Zm cross Zm cross Zm. Okay, but it's not only that we have this, like it's not only a set of distribution. This distribution should be compatible, okay, in some way. So let me, okay, of course, this is kind of thing that Jihan already explained, but it will be good to explain again at the beginning. So where they are, I mean, all these distributions, they are compatible. So what we mean by compatible are and this what exactly encode the things that we say that this is a morphism, okay? This encoding by saying that this is a morphism. That means that if we have, let's say, okay, maybe a new page. Let's say we have this x here, x2, x1, x0, and so on, okay? So let's say we have some symbolic here, okay, which means it's triangle A, B, C, okay, for this, like a context for this three measurements, A, B, C. Let's say we have someone here. And let's say that we have someone here, tau, let's say, that is have the same C, okay, like CE, let's say. So this should be gluing here, the same thing. So the picture will be like this, right? If we, okay. Here all the simplics and how they glue together, okay? And which collapsing and which is, but if there is a realization for every simplicial set, so in realization, there will be part of the realization will be this, okay? Because it's glue and C. And what happened for their distribution? Because we said that for this one, there is a distribution here, P sigma, where in distribution on Zm3, right? And for this one, there is a distribution on cross Zm, yeah? But because we have here a simplicial map, this is a simplicial map, so if we can go from tau to C by taking, like we know that this is tau, we know that D0 of tau, C. So if we going like to D0 of tau, which is C, so here it's give me the distribution in here, right? But because of this is exactly to say that it's simplicial map, that it's exactly if I apply here D of D0 for this one, okay? What Jihan explained last time, we can D also act a morphism, okay? But in the same time, we can go by this one also to see, right? Like we can here, let's say this is the order, just a minute. How we can go to C, we have to apply twice, like, because if we take D0, we will get this one, right? This is D1, by the way. I have a mistake here. D1, we will get C, yeah, D1. Okay, anyway, okay. If we D0, we will get this, and then we apply D0 again, we will get C. So D0 twice, by applying D0 twice, D0, and again D0, we will get C. We will get D0, D0 of sigma. This one is sigma, which is C, okay? Which is C. So this will get this distribution. But if we going like this, and we taken this distribution, and we apply on this D0 as here, the same as here, this is exactly what's saying to be a simplicial map, then we get the same one. So what we can get here, because of this, because of this glue together, these two simply to go together, so we will get the following equation. what is the following equation? The following equation says that P sigma, if we apply on this phase of distributions, the marginal is the same as this one in BilTop. So it's equation. We will get equation. So we'll get many equations. So we can say here, like we can back again and say that we have here many distribution, but there is some equation between them, okay? This is what means the compatible. Was all, if you back to all the approaches before, was the approach to deal with this phenomena mathematically, to write some equation, which called the non-signaling equations. Of course, this is one equation, but it can be many simplexes that glued together, then we have more and more equation. So what good in this language that Jihan started? It's what the good things is that he encoded everything in one map, and we want to use this advantage that this all encoded in one map. Okay, this map, inside this map, because it's simplicial map. This exactly saying that it's compatible. This exactly saying what I said here, that there is a relation between the distribution, and not only distribution here and here. There is a relation between the distribution. Maybe someone here, maybe it's good to say it's for practice, because it will be good for the next talk, maybe not for this talk, but maybe someone notice that this, like the distribution, for example, we have distribution on this also, right? Like, let's say this called it's gamma. Gamma, it's exists here, right? So we have distribution also for gamma, but we can get it from the distribution from sigma, right? Because we can apply on this, like, let's say 0, 1, 2, this is D2. So this will give me this. So we can write here that it's important, one can note that like it's important to know, or it's enough, let's say, not that it is enough to know the image of the generating one. Like this one, it's not generating, it's because it's a face of something else, okay? Like when we have simply, there is some of them that it's not a face of anyone, and it's not a degeneracy of anything. So it's called generating. So it's enough to know the image of the generating simplices and how they are glued together to each other. Yeah, is that enough to know in practice, in many practice, but for the theory, it will be good to see all of them together, because here we will have also like some, I didn't talk about the degeneracy. For degeneracy also we have, like, every distribution will appear also again with some zeros. Maybe you will see this with Salman next time. With some zeros that it's seem like, okay, it's additional, like there is many distribution here, because there is, even if we take like is that generated by x to be generated, this is what we always doing, generated by finite simplices, but because of the degeneracy there will be infinity simplices, so there is infinity distribution, and most of them is coming from some only finite number of them. So why we write it? The goal is to encode all in one morphism exists in here in simplicial sets, which is like non-category. Okay, non-category, and people started to work on this in homotopy theory and in category theory, like maybe 70 years ago or something like this. Yeah. So we can take advantage of this. Okay. So let's say now our goal in this talk is to understand goal is to understand the algebraic structure of simplicial distributions. Okay. Let's fix x and y. Let's say we have some x, which is the measurement space, and y, the outcome space. Let's fix all the illustration. What it's I forget what Jihan with notation used Jihan last time. Maybe this notation or this. We use always this notation or this to say that all this mean all the set of all. No, without the like. Usually in papers we use this or this. Okay, the same. Okay, that mean all the simplicial distribution from x to y. Okay, that mean this set. Okay, or P is a simplicial distribution. P simplicial. The thing here is that this is not only a set, it's a convex set. Actually, this is clear and people know about this. Like we can take some distribution. What does mean convex set? I guess all of you know what it's a convex set. Convex set like this, for example, set. It's not convex because I can take here one point, other point, the line between them. Some it's not here. Yeah. So here we can do this. Like if we take some distribution P and other simplicial distribution Q, and we take like 3/4 of this plus quarter of this, this will be again simplicial distribution. Which notation you used last time? This one or this one? Can I use this? Is okay?
I think I use both, whichever you want.
Okay. Maybe I forget. Yeah. So this will be also simplicial distribution. It's known. It's not hard also to prove. You know. Yeah. So this will be simplicial distribution. So what is the definition? Let me give the definition of convex set. So okay, maybe not with all, but the definition of convex set definition. A convex set, let's say X is a set with an operator from 0, 1, x to x that's satisfying some, which satisfying some some properties, some conditions, some conditions. First, like for example, we have it's here like if I take alpha x y is the same as 1 minus alpha yx. What do we mean by this? Like we mean here, we have this convex combination. We can do convex because what we mean by this, another way to write this, and this is what we usually writing. Instead of this, we're writing alpha x plus 1 minus alpha y. But usually convex set, it's inside the vector space or inside Rn. Usually we're working in convex sets that inside this, but this is abstract definition of this. It's not have to be inside this. So this alpha x by itself, there is no meaning for alpha x by itself. There is a meaning for some convex combination. When we have a number between 0 and 1 and two pair of element inside x, okay? Then this can give a meaning inside x by this operator. Like this, we mean this. But this by itself or this by itself, it's don't have to. There is no meaning for this because we are not inside a vector space. It's not sure. So this is one of the condition. Other condition, it's this condition. It's so makes sense, right? Because it's mean like if we do, it means that it's like commutative. Like if I'm doing now 1 minus alpha y plus alpha x is the same. Of course, it's the same. Yeah. And like another thing, if we did this, what we get? Like if we did like a convex combination between x and itself, so we will get x. Third, which is also easy, it's if we 0xy, what it's give me. Or it can be written 1xy, it's the same, like 1xy, what it's give me? It's give me x, of course, again, right? And there is other condition I will not write now because it's long, but I don't want you to focus on this. You can find in the paper because it's not like our issue in this talk. But I want you to understand that instead this is kind of abstraction, like we go into something more abstract, like convex set, what we know that inside R2, inside R3, or inside Rn, or inside any vector space. But one can define this by properties without being inside some vector space, by properties like this, what we have now, okay? Some conditions. Okay, this is, we did it more abstract. But there is another way to do this that it's much more, it's equivalent, but it's like much more general point of view as an algebra over monad. Okay, so let me tell you what I mean by this. We see that we have this what called the distribution monad. We use this D, the distribution monad. And we know already, okay, from this name it's monad, but it's like we already use that the functoriality of this because we see here that we applied it not only on sets, this D, but we applied it also on morphism, on the faces map, right? So this is what allow us to apply this on simplicial sets, okay? So D, this D is a distribution. First of all, is the functor from the category of sets to the category of sets. But this is more than a functor, actually. This is more than a functor because it's equipped with important it's equipped with this, sorry, equipped with the units, like for every set X, we have from X to dx. This is called delta, this map. This map, like every X can be thought as a distribution here. Like it means that it's included, like X included in that distribution, because we can think about X as distribution here. Which distribution? The distribution delta X. This known one that everyone, you know this. It's the one that give delta X of and like if we have Y here, only if Y it's equal to X is 1, otherwise it's 0. Okay. This delta, it's a distribution, and also we have some average of distribution. If we have also a map of average of distribution, like if we take the distribution on distribution, we can down to distributions. This is injective and this is a projective map. This is some projection. What does that mean? Like if I have a distribution on distributions, then we can make some average between them. Like Q, it's give me a number between 0 and 1 for every distribution. So if I put here some distribution P, not simply some distribution, I'm going to all the distribution in dx with P, okay? This means some average of this distribution give me a new distribution here. Okay, we have these two maps. This is called mu x. Okay, this one is delta x. Sorry, let me write here delta x, and this is mu x. And in fact, this map makes it a monad. Okay, what that means? It's have some good properties. First of all, there is some questions for now. Or to ask something? Okay. Yeah, which properties it have these maps? It have the following properties that this this is act like a product, like multiplication, and have this property like it's if we take d of d 3 times on x, and let's say we apply first of all like mu of dx. Okay, mu of dx, because we can't do this like there is twice, so this way we will go to dx. So we apply mu on this in order to product both of this in order to get d, and then we apply mu again. We will get here, but we can do the same by applying here, like we can apply first of all mu on this, right? So we can go to mu x, but there is d that act on both. And then apply mu. This will be the same. Okay, that means that mu is this product is associative. This means, okay. And this unit is play the role of the unit in the probe, because what that means? That means that if we have something like d dx, and we apply this on dx, dx, yeah, and then we do the product, this will be the identity. Yeah. And if we do is the other way around, like if we do now d of delta x, that also we will go to dx, and then we do the multiplication, this will be also the identity. That means that this plays the role of the unit. That's why we called it the unit, this delta x, and this we call it the multiplication. Okay, this is a general phenomena that happened also. There is many other functors that have could by these maps, something like this, and have this property. We called it monad. So that makes, which means that D is a monad. We called it distribution monad because it's known as a monad, is a monad. So a monad, the definition of monad, when we have not only a functor, there is a map, like we can represent every one here as distribution, and we have such a map that called the multiplication with the following properties, that meaning largely the multiplication is associative and this is really the unit. Okay, so this called the monad. So when we have a monad, we can talk about algebra over monad. Okay, because actually if we talk a little bit about what it's mean to be dx, what does that mean dx? Let's say d of, let me take three x to be 1, 2, 3, or ABC. What that mean to be d of ABC? That mean all the distribution on ABC, right? But that means that I have to give a number for this B1, a number for B, a number for C, right? Where the all this number between 0 and 1, and the sum of them is 1. Yeah, but geometry, it's mean this triangle, only triangle, right? A, B, C, right? This means only this triangle. Because like if I take, for example, 0, this will be a half, and this half, and this 0, that means exactly this point, right? Half of this, half of this. If we take, I don't know, a quarter of this, half of this, and a quarter of this will be something that more close to be something like here.
Okay,
Yeah.
I have a question because this picture might easily be confused by the simplex picture that you drew earlier. So this is something completely different.
Yeah, it's different. Yeah, I will come. Yeah, it's
Yeah.
completely different. Yeah, right. It can be
Yeah.
this, but I will. When I continue, you will see what I want to say. Like, yeah, exactly. Right. You are right. It's very simplex. Yeah, and if we take 4 point, actually C D, it will be the one can see that it will be all the a pyramid. Okay. Pyramid like this. Okay, but exactly like this is the delta 2, what we call this delta 3, but this is a free. What it's a special of this, that okay, it's a convex set. Okay, this is a convex set, but this convex set, it's called the free. Why it's a free? Because everything's like independent, like it's generated by this freely, like every point here, it can be written uniquely as a convex computation by this and this and this, not in one way. Like, but there is a convex, like let's say this also is a convex set. This set is a convex set. But for example, this point I can write as a between this one, or maybe in the middle, I will take something in the middle. That's maybe half of this plus half of this I can take, but maybe I also can write it in another way as maybe half of this plus half of this, or something like it. I don't know, like a quarter of this and 3/4 of this. It depends where this is. So we can write it in other ways, right? Okay. So it's not like freely generated by these vertices. Okay. This is the difference. So this D of this, it's give me only things like this. Like pyramid here, it's not good pyramid. Like I meant something like this. Yeah. Okay. So this will give me things like this, freely independent, like vector space. Like we know that in vector space, there is a unique way to write when we have a basis, right? But we know that, for example, in all of you know groups, right? All of you know groups. We know that there is the cyclic group is too easy, but there is also groups that generated by two things like A and B. So we know how it looks like this group that generated by these two, right? We know that it's things here will be something like this, like everything that we can write in this way in by A and B. It's easy, but we know that there is some group with relation, like not this is some with some relation between, like they asked me that A, B, it's equal to A to B, A. Yeah, some relations that make it some more complicated here, there. So this is also in convex sets. This is the difference that when we have something like this, like say, easy simple exaggerated by Kleisli, like triangle or line or this line or what I say pyramid, like all of these are, it's easy convex sets. It's like have three bases like the vertices, but we can have something more complicated, something like this convex set, or yeah, right, or something else like can be this is a difference. How we can get this using this distribution monad? So the way that people doing in not only in convex set in order to for this, but for many algebraic structure, what they are doing, they said, let's imitate the behavior of dx, right? Like dx is, we say that d of all the distribution, it's some free convex in this sense, like what we explained. But if we imitate, like if we try here, I can here copy paste, right? Or I can't, just a minute. If I do that like this and then, no, okay. If we now replacing this, what we have for dx, what we know that dx, we have a map from d dx to this mu x. This is the map that give me the convexity of this dx, but freely. But we can replace, if I have some set u that have such a map from d u, like we replace this dx by u, okay? We replace this dx by u, this by u, and we want to replace it here, okay? So let's replace it here. So we will have, and there is a map, like let's call this map by u. So we can replace this by u. And here's this one mu x by pi, and this one by u, and this by pi. Let me replace all of them. Okay, pi, u, and this will be also u, and this u. And this one will stay mu. Let me mu u, mu of u. This one it will be, and we will get this property. And here we can also replace by u dx. This by u, this also by u, this will change by pi, and this will change by pi. So here we will have u du delta of u, here pi, here u. If we replace this, will give me the same things, by the way, because this will be pi, and this will be u, and this will be only delta u, because we don't have this t as before. Yeah, so delta u, this will be the same as here. So we will have this. So this is the idea of algebra over sets. Like we try to imitate this one, like this is the free one have this map mu, but we replace it by another map. If there is a map pi that have these properties, let's make this two diagrams commutes. Like if we going like this and like this is the same, and here this is the identity. So then we called it algebra over D. Okay, so this is the definition of algebra over D. To be U that equipped it with a map pi like this, where this diagram commute. Okay, again, the philosophy behind this is to behave like the free one, like you want to behave like dx. If it's behave like dx, so it's very good, it will be algebra. But of course, this algebra will be, it's don't have to be something free like this. It's as a relation here between this, can be some convex sets like this. Yeah, here, like instead of doing relation by equation, people find that there is a way to do this using diagram. Okay, inside the diagram there equation, but really it's many equation inside this diagram, and it's this also like this is abstract mathematics. Like they try to make many phenomena in mathematics that people thought about this as different. Now they are the same phenomena, and we have this phenomena of algebra over monad. Okay, so this is a good way for us to continue that to think about what we said before, that simplicial. We said before that the simplicial distributions, there's a simplicial distribution to y, it's a convex, but now we can say it's an algebra over the distribution monad over D. Okay, think that it's algebra over D, because D, it's coming from the thing that D act on sets, like it's a monad from set to set. Okay, but we want to understand all of this together, like all. We want now all for every x. So what is the structure? Everyone is convex. Okay, but what is the structure of this when we have now xy as a category, like when we like the object will be xy in simplicial sets, and this is morphisms. Okay, so as a category we want to understand all the structure. Okay, every one of them convex set, but this is one thing. But what is the whole structure? What about the composition? Which kind of composition, which kind of can be done here? So this is the other issue. So this point of view that H algebra over D, this can be helpful, because it seems that the distribution monad, it's not like any monad, it's have some other property. There's some other good properties, that it has some multiplication, natural multiplication. What I mean, like, okay, for every, if we have given, say, x and y sets, so we have a map from dx dy to dx cross y. Okay, that means that if I have here two pair of distribution on x and y, we can have one distribution on the Cartesian product. What that distribution doing? Actually, it's m pq. So easy, the formula of this, it's only px qx. One can check that really the sum here will be 1. If we don't, it's easy to check, and really it's this will give us a multiplication. This multiplication, first of all, is natural. Okay, this is natural. Let me tell you what that means, that it's natural. It means that if we have, it's not only like work in, it's also for morphism, it's good for morphism. Like if we have such a map from x to x prime and other map from y to y prime, then like going like this by this multiplication, and then here we can apply this, like we can apply d on f cross d on g to go to dx prime dy prime, and we can apply this, the multiplication corresponding for x prime y prime to go there, and we can apply the multiplication then to apply d of f cross g, because we can get, if we have two maps, we can get the map f cross g. So this commutes, okay? Like going like this, applies this map, then applies this map is the same as applying this map, then applying this map. This is one of the property. It's called naturality. One of the property. The other property I will write now the good property of this and what is this good property help us to do, okay? First of all, let me write the properties. The other property is that this multiplication is associative. In that sense, like if we have dx, dy, dz, we can do, first of all, we can apply m of xy and only the identity on dz. So we can going by this to this thing. Then we can apply mx cross yz in order to get this distribution here. But we can do this in the other way, right? You can guess what I mean, like it's myz. It's exactly what's called associativity, right? So this multiplication is also associative. And we can go to here by doing mx y cross z. Okay. So this associativity, three, the other thing is that it's also because we said that there is this not only a functor. So far we're talking about it as a functor, but it's also monads that have this unit and multiplication. It's work good, like this multiplication, it's good with the unit and so the third, maybe I can write together the things that if we have like x, y, okay, we can go by this to dx, dy by applying this unit. And we can then doing the multiplication, right? But this will be the same as to take the delta xy. So that means like this is generalization in some sense. This is generalization of the Cartesian product. Yeah, this is what that means. The other thing also for the multiplication, like if we have here d of dx cross d dy, we can do mu of this and the mu of this to going to dx cross dy, and then to do the multiplication. But on the other hand, we can going, I want to go from this now to, maybe I wrote it somewhere. Yeah. No, it's okay. Anyway, it's dmxyd. Yeah, I want to go. Yeah, we can do actually here, we can do m, but m of dx dy, right? Dx dy, right? We can do this m, and in order to get d of dx cross dy inside, and then we can do dm, like the m of xy, and apply d on this. So this will give me d of dxy, and then like this is the m for these things. Okay, this is the m that we have to apply 2 of m like this in order to get this, and this is commute. Okay. M of m of x cross. This is commute. So that means that it's behave good also this multiplication with the monad structure. Okay. The monadic structure that we have this multiplication and delta. So this actually leads, this thing leads to be able to compose this multiplication with another composition, and then we can go from saying that D act on sets into saying that D act on categories. to be honest, on small or even locally small categories. Yeah, this is locally small categories. How are we doing this? We say that, let's say that we have a category given C in category. We now built a new category. We call this DC. How this is category work? Like the object of this object of DC will be exactly the object of C. But for every two object in C or in DC, the morphism between these two objects will be by applying D on CXY. Okay. By applying this, and one can ask what is the composition here, because this is the thing that how we can define the composition, because what is the composition we need to, if we have X, Y, and Z, so we need the composition, it will be from here to DCXZ, right? So how we can go from here to here? It's by using the this M we talked about. So if we apply this M, like M of this and M of this, so this will, we can go to CXY cross CYZ. And then we apply D of M, D of the composition, the normal composition of this is the composition in C, the original category, okay? So this will be the definition of this composition. We will call this composition usually by this, okay? This is the composition. Yeah, so this defines this composition. Now, of course, one should here check that this really give us a category, like we have identity, we have this is associative. Also, we should define on functors. On functor will be the same, like the same on object, like the same functor, and we apply D on this. So it's something similar. So why it's work? The property, actually, these properties of the multiplications that used in order to define the new composition, this will be the key in order to prove that it's work. Okay, I will not going to do this now. Of course, there's no time, but the key is this properties. Okay, so here we can we see that for a category, if we have a category, what we did here, if we define for every category a new category. Okay, let's call this the free convex category. Free convex category. But actually, it gives us a functor. This is a factorial, like this is a functor from categories to categories. So we now, D was acting on sets, now it's acting in category. And one can show that it's also monad, like with the same multiplication, and can be used and unit to show that this is also a monad. So in fact, this is a monad. So because this is a monad, we can talk about algebras over this monad, and this is the definition of convex category. Okay, so let's give the definition. Convex category is an algebra over this monad. Like a convex set is an algebra over the monad when we acting on set. Now, no, we are on category, because this monad can be seen as a monad on category, as we shown, as shown before. So the algebra over this monad is called convex category now. Okay, this is a definition of convex category. So what does that mean to be convex category? So what does that mean if I have a category C to be convex category? That means that I have some functor from the free category to here with the properties, if you remember. So this will be functor now, not only because we are in the not only a map of sets long. This is a category, and this is a category, and this functor with the properties we said before. But actually, what that mean, like this functor will be the identity on object and act on this. But in fact, like this means that to be a convex category, let me write it in a new page. So C is a convex category if and only if for every objects x, y, C x, y is a convex set, but also they are acting together in good way. What's that mean? Plus that if we have x, y, z, for every x, y, z, let's say, if we take the composition in this category, and we have, of course, for everyone structure of being like this pi that corresponding to this one from here. The same here. D of 6, sorry, 6y. We have pi here, we have here pi and pi. Okay, there is like pi cross pi. And here we can compose by what we said before, what we call this star. This is a composition we defined before this one. So this will be commute, okay? This is commute for every xy. Actually, this is like it means this one. It's because actually here, yeah, this is one issue that the product is also give me tensor product here, the product of convex sets. But this is something that it's weaker than to say that it's enriched by to say that this one the composition it's convex. No, it's not mean the composition it's convex. But if we take the like if we divide this product and take another tensor product, this will be really enriched by like this can be seen that algebra over all convex category. It's really the category enriched by convex set with another tensor product. We're not going to talk about this in this talk, but we want this point of view. And let me now show you after all of this, like maybe the main result in the paper. Okay, the main result. First of all, this we can now say that the simplicial distributions, all of them, like if we take this category, the category with simplicial sets as objects and simplicial distributions as morphisms. Okay, and simplicial, let's say it's right, it's exactly, it's better, and simplicial distributions as morphisms. It is a convex category, okay? So this is a structure, actually. It's a convex category. For the composition, it's non-composition, it's a Kleisli composition. The composition will be, if one doing this, it will be like the composition here, like if we have x, p to dy, and y cube, let's say, to dz. So the composition, we'll write it like this, from x to dz. This will be like in z, this will be this, to take, this is exactly to go by p, and then to apply d on q in order to go to dgz. We apply d on q and then apply mu. This is known composition called the Kleisli composition. Okay. This is the composition in this category, what I described before. Okay. So this is a structure actually that we have for all simplicial distribution. To be honest, so far it's not applied like this whole structure. Of course, we apply that it's convex, so but this morphism, it's not really applied for a real computation so far. But the things that applied, yeah, maybe let me say something before I'm going. It's more than this, actually. It's more than this. I wrote here before I forget that even this map that Jian defined last time is, by this map he defined contextuality, right? From D of a simplicial set from X to Y, right? This map. Actually, it's coming like as a part of a functor. There is a functor from theta from this, like this category, what we describe, what we can call this category. Let's call it simplicial distribution. I don't know, maybe call it by some name. It's because it's a Kleisli of, yeah, of something, yeah. Okay. And this is the free one on simplicial sets. We apply D on simplicial sets. This is a functor.
But the target is just
Functor
slightly on the simplicial.
in the what? Sorry.
From your description, I understand the target is just the Kleisli category on
Yeah, exactly. This is a
network.
Kleisli. So maybe we can write like this, right?
Yeah,
Right. We can write like this. Right. Yeah. So this is a functor, or even like morphism in the convex. This is inside convex categories. Okay. Like not any functor that like preserves the. Even not only this, like inside convex category, and this also inside convex categories. Okay, this is the convex categories. Okay, but this is not like this is good for the theory. I don't know, but this is not applied so far. So what can be applied? It's and really we use this in other papers. This when we look at convex monoid. So let me briefly tell you what I mean by convex monoid. Yeah, I will have another 10 minutes in order to finish. So we talk about convex category, like monoid, we can think monoid, it's a category with one object. Okay, so as definition of monoid, it's easy, but one can think about this like we have maybe easier way to think about convex monoid. It's like there is a monoid, like we have some multiplication there with units. Associative, there is, okay, it's convex monoid, like M is a convex monoid. What do we mean? Like M is a monoid. What that mean to be a monoid? To be like there is units, and the multi is associative. Okay, there is a multiplication and the is a product, and the product is associative, and there is a unit. Okay? So this is what means to be a monoid. It's less than a group, okay, to be monoid. And the other things, it's plus M is a convex set. But of course, like when you doing like this mixed structure, you should add the conditions that connect between the two structure, right? So the thing that it's if you have like if we doing alpha m 1 plus 1 minus alpha, this because it's convex, it's well defined. Yeah, we can talk about this in M, and we can product with some M, right? So this product is the same as to doing this, to take this one object and to take this object, and then to do this. Of course, also from the other side, it's the same. Okay. So this is a property that connect between the two structure, but one can define also this in other way to say it's only a convex category with one object, convex category with one object. So why it's good, the convex monoid? Because actually in convex monoid we can define something. It seems like related in convex monoid. Not everything is invertible, right? Not every element is invertible inside monoid. Like because here it's not a group, right? We say it's a monoid. It's this properties, but in a group we add the properties that for every M we have some inverse, right? That give me the unit from two sides. Yeah. So we can, someone can write this is the invertible inside M. And one can ask about, can define something called weakly invertible, like which element, it's not invertible maybe, but it's can written as a convex combination of invertibles. So we can do this, we can say like, okay, M have this dm, this pi from dm, but here there is inclusion. Yeah. And we can ask who in the image of this. So let's call maybe this map, I don't know, T. So T, something like, okay. So the definition of weakly invertible, M is weakly invertible if M in the image of this T, okay? Like it can be written as a convex combination of the invertible. It's not by itself, should be invertible. So every invertible is weakly invertible, okay? So it's really something weaker than to be invertible. And why this is connected with our issue? So it's the thing that simplicial distribution for x, y, but we like what we use this delta zm or nerve of zm, but both of them have a groups structure. Like it's not only simplicial set, it's simplicial group. That means that because we see like that M cross ZM. This is a group, right? This is a group, and this map that by deleting we say this is a morphism of a group. This is only projection, right? So this have a group structure. So we can say simplicial group. Yeah. And if we apply D, this will be monoid. If we apply D on this, and in fact, all of this will be monoid, convex monoid. So okay. So because of the group structure in Zn, this will be a convex monoid. Is a convex monoid. Don't confuse. We said before that all this convex category when we mean all of them. Like when we take all this something else. The product was with outside, like no, we here fix X and this. We fix both of this. By the way, we can choose Y to be any simplicial monoid or simplicial group. I forget. Yeah, a simplicial monoid. I think it's enough. Then this will be simplicial. This will be convex monoid.
I think there's an additional D, right, on this S dist X D delta. The D
What additional what?
Yeah, D there, right there.
Yeah, additional D, right? Because sometimes, okay, we can. Yeah, I mean this, or yeah, or what Jihan said, right? Yeah, simplicial distribution of X, yeah, delta Z, right? Because it can mean something else, right? Of course. Okay, so this is a convex monoid, and here is the main theorem of this paper. It says that because we can talk here about weakly invertible, right? What it's mean to be weak invertible, or weakly invertible, we call it, right? Weakly invertible or weak invertibility. So this coincides with non-contextuality. So here is the theorem. Given simplicial set X. And even not only this, any simplicial group, it will be right, okay? And simplicial group Y, then if we take simplicial distribution here, is non-contextual if and only if P is weakly invertible. Okay, so that is this is the things. Maybe next talk we can do this, like show in practice how it look like this product that we're talking about inside here inside the simplicial, how we take some simplicial distribution with the same outcomes, the same like this is the outcome, let's say, and with the same measurement space, how we can product to one can see. So there is some examples in the paper, but maybe we can talk about this later. I prefer now maybe to take some question if there is some question is the rest of time. So that is finish.
Thank you, Aziz. Any questions?
you.
Any questions for Aziz?